Hi, my name is Matt Fiddler, and I'm here to talk about nlmixr in behalf of the entire development team. nlmixr is an open source nonlinear mixed effects modeling package in R that focuses on pharmacometrics. I want to talk a little bit about our team. Our team is multinational from California to the Netherlands and multi-company covering CROs and big pharma. We started our journey in 2017 when Wenping submitted the first nlmixr to CRAN. We released a note to the modeling community through the NOMM users group. And from there, we've gotten community involvement. And with the community involvement, we are able to handle more robust types of models, find some bugs that we had and fix them, and to get a better install experience for all users. We think that this is something that is useful to the community and something that we would like to use going forward. Our vision is to develop this R-based open source nonlinear mixed effects modeling software that can compete with commercial pharmacometric tools and is suitable for regulatory submissions. So the question becomes, how are we doing? When we compare it to large commercial tools like NOMM and Monolix, FOCEI and nlmixr runs faster than NOMM. SAEM and nlmixr runs as fast as Monolix, and both are faster than NOMM. The parameter estimates for all three NLME tools were similar between all of the software tools, both in terms of population, the between subject variabilities, the residual errors, and of course the standard errors. We also know, because the FDA had highlighted it in their ACOP presentation in Florida, there was one successful approval to the FDA with nlmixr. I just want to cover a few things in this talk. First is the modeling syntax for nlmixr models. Second is the goodness of fit plots. And third is, once you have a model, how can you simulate new scenarios? So first part we're going to drill in about is the syntax that you need to write nlmixr models in, how you run them, and what the output looks like. In general, most people are familiar with NOMM, and you may have heard of NOMM. But NOMM and nlmixr share a few things in common. They both have parameterizations. They both have fixed effects parameters, initial estimates for those fixed effects parameters, and random effects, and an error model that you can describe. nlmixr is no different. You read in a NOMM sort of data set with some things that are expanded, like you can name your compartments to make them easier to refer to. Then you have a function in nlmixr that has initial estimates of the population parameters, initial estimates for the between subject variability omega matrix, and the initial estimates for the error model. And the model itself, which shows relationships between the fixed and the random effects, as well as the model itself. In this case, it's a closed form solution, linear compartmental model that's modeled by an additive unexplained variability. Drilling down just a little bit further, this initialization block is the first thing that you typically specify in a nlmixr model. Here you can use the basic R syntax to declare what the values are for each of the individuals. You can use assignment, just like in R, or equals, just like in R. And then if you want to, you can label them with the label keyword, or you put the label in the quotations and tell you what the label is. Or if you wish, and you're running an interactive session, you can label it with a comment. When you label it with a comment, it won't work in R command batch. Those labels will be dropped. For the random effects, you use the tilde operator. When we model the omega block, we're using the etas are modeled by an omega block. If we're saying there's correlations between them, we can add the two as a pseudo way of declaring which omega pieces are there and specify the lower triangular matrix. This is similar to a block structure in NOMM. In nlmixr, the model statement shows the relationship of the fixed and random parameters, usually first, and then it shows the the model itself. In this case, it's a closed form solution and says it's modeled by an unexplained residual variability of an additive error or just normal residual variability. When we use this linear compartment model, it derives what type of model is being performed by the types of parameters you use. If you use CLV, for instance, it's a one compartment model. All these parameterizations you see on this slide show different types of ways to do a 1, 2, and 3 compartment model. They also use parameter aliases. For example, instead of V, you can use VC or V1 or V2, Q. The parameter case doesn't matter, and you can actually look up some tested parameter combinations that work for each of the linear compartment models. You can see at the very bottom of this slide, it has a place where you can go that shows you these different types of models. You can also specify ODE solutions. This is more important in cases where there's no closed form solution or it's not readily available, or a PD model where an ODE is required. So in this case, we specify the clearance, volume, and Ka relationships between the fixed and random effects first, and we then specify the ODE model. And it's the same that we were having in the linear compartmental model, except for it's described in terms of ODEs. You notice here that these parameters are additive expressions. So your typical value of your parameter plus your between subject variability. This is what we call an nlmixr mu referencing, similar to what they have in NOMM as mu referencing. When you have this mu referencing, it can run in SAEM. In SAEM, all parameters are required to be mu referenced. You can also add additional pieces to a model. For example, you can add bioavailability and lag time. They're done as compartment properties. So if we have a depot compartment, we would put F of our depot, which means we're applying a bioavailability to all doses inside the depot compartment. And the same thing is true for central if we were to do that for central. But it depends if there's any doses that are applied to the central compartment. A lag for the depot compartment shows that there's a lag time in the depot compartment, and that is also just basically a parameter property. Last piece that I'll briefly talk about is the residual errors. In the model itself, when you are describing an endpoint, say concentration, you can model it by a residual error component. In this case, you would say Y is modeled by additive standard deviation, prop or proportional error, additive plus proportional, log normal, power, additive plus power, additive plus Cox, additive plus Johnson. Turns out that this is also supported for multiple endpoints like a joint model. If you had a PK component like concentration or an effect compartment. The next thing I'd briefly like to talk about is diagnostic plots from an nlmixr model. Briefly, if you use plot fit, it will give you a variety of simple diagnostics that can be used to try to look at your model quickly. It looks at trace plots, DV versus pred, or DV versus IPRED, residuals, and individual plots. There are a few others. At the same time, if you want a specific type of look and feel, you can use expose using the package expose nlmixr, or ggpmx, which also interacts with nlmixr. Both allow different types of plots for both expose nlmixr and ggpmx, and these plots as well. They're ggplots, so you could modify them as well using the standard ggplot interface. Last part I'd like to talk about in nlmixr is how to simulate once you have a model. So first I'm going to talk about multi-subject simulation, simulation without uncertainty in your model parameters, and simulation with uncertainty in your model parameters. So we're just going to take a brief excursion into RxODE. So RxODE is the ODE solving engine that powers the estimation methods of nlmixr. So ODE solves the ODEs, and nlmixr uses that information to estimate parameters. So the question becomes, what do I need to know about RxODE? What in RxODE is used by nlmixr? And what RxODE is output by nlmixr? So just as a brief aside, we can actually specify doses and new dosing scenarios if we want to simulate them. If we want to say simulate a side-by-side comparison and having comments what they do. So if you have an event table, you can access the add sampling and add dosing functions with a $sign interface. This $sign interface allows you to add sampling times with the add sampling or add dosing times with the add dosing type of idea. In this case, we have add dosing adds a dose amount, the number of doses, the dosing interval, what compartment to dose to, what type of infusion rate, and the start time of the dosing. In case of the ET for the event table function, you can simply put the sampling time, or if you name the compartments that you're going to put these in, amount would go in the dosing amount. ADDL is a non-mem type that we would use. It would be the number of doses minus 1. It's the additional number of doses is what it's called. And then the dosing interval. The compartment is where this doses to, infusion rate, and the starting time. In the code below, we created an event table where we have 10 BID doses of 1,000 or 10,000 units and milligrams, and 20,000 milligrams events you're studying for 5 doses that are 24 hours apart. Okay, going back to nlmixr, once we have these event type of tables, we can use the model that we already ran. We're saying the ODEs are actually specified in the nlmixr piece of this model, this function in the model block. Then we have this dosing and sampling, and then we simulate the event. So n would be the number of events you're studying. So, and then eventually you would just use simulate the new events and the number of subjects. It'd be n times n, and this n times n is 300 times 300. So you're actually doing a larger study, but this is so we can compare with the uncertainty simulation, which we'll talk about in a little bit. Stimulation output will give you the simulation ID, the time, the individual predictions, and the simulations. So for example, if we look at this particular simulation output, it gives you the params values, which you can look at that and you can see when you summarize it that there are constant population parameters in each of the simulation IDs that you have. You can also see that this has initial conditions and is also a data frame that has information in there. When you decide that you've done this simulation, you can plot it using plot, and it will give you a plot sort of like this, where it has the X label, the Y label, and then you can use a theme to make it so it's not quite so dark or light. And this allows you to show what the simulation with this new regimen, this BID regimen with the Theophylline could be using no parameter uncertainty. If we want to have uncertainty in our parameters, that means with the model we have, we assume that we don't know it well. We use the standard errors and the information we have in estimating to sample from the multivariate normal distribution and from the inverse Wishart for the omega and sigma matrices. With that information, we simulate a new trial with this new event table, and the number of subjects would be the number of subjects in each trial. The number of studies would be the number of studies you simulate, where you sample each time from a new population. Now, in this case, you can see that the number of subjects times the number of studies would be the total number of subjects simulated. So when we looked at the last simulation, that's the reason why we did n times n, just to make them comparable. Simulation output is still simulation ID, time, IPRED, and sim. Using this information and taking a summary again of this params block, we can see that the KA, the TV, and the CL actually change based on whatever study you're in, which is what we were hoping for. The other thing you can see is this realization of each omega and sigma matrix. You can see it by looking at the omega list and the sigma list. And these are sampled from the inverse Wishart, where in this case, the degrees of freedom is number of subjects for the omega piece, and the inverse Wishart, where the degrees of freedom is a number of observations for the sigma piece. As you simulate a new plot regimen, you can see with the same syntax, you get a similar sort of plot, but you see higher absorption uncertainty, which correlates to a higher degree of uncertainty in our parameter about this Ka piece. With that, I'd just like to take a brief moment to talk about what's coming in the next releases of nlmixr and RxODE. We are moving this nlmixr fit function to be something you can use to run RxODE models. This takes a large rewrite of the code. We want to make sure that since we're rewriting it, it could be that the codes are incompatible between the versions. And since it's such a large rewrite, we just wanted to be clear that nlmixr2 and RxODE2 are thought to be compatible in most senses, but are slightly different in many ways, enough that we would want to rename the package. One of the things that we did in this, we're doing in this particular release, is dropping the requirement for mu referencing in SAM, which is one of the reasons why we rewrote this interface and put it into RxODE. We also are doing simple, more consistent simulations between nlmixr2 and RxODE2. That means that one model function can be used for both pieces. We're looking at consistent interface between all the estimation control objects and simplified a lot of code to allow more extensions. And we're starting an API or a way to interact with nlmixr that's more well documented and can allow more extensions by various people. In case you want, there are some documentation pieces and further reading you can look at. You can look at the home of nlmixr, where it is GitHub nlmixr development, or if you want to look at what we're doing in the new version of nlmixr as we're preparing to go to CRAN, you can look at GitHub nlmixr2, which has the RxODE2 underneath it, and we also have expose nlmixr as well. And we're always going to have nlmixr.org have a documentation. As we use this new nlmixr2, it will automatically be updated to the right place. The other part, we all have our course material open. This will be open as well. We have a Twitter handle at nlmixr. We have a LinkedIn group that you can join if you would like. One thing that we're going to do at the end of this is talk about this nlmixr demo, which is a larger demo that looks at a classic example of warfarin in a multiple endpoint model where we have both PK and PD.